Welcome to the Explainer. Today, we're diving into a breakdown based on the lecture by Dr. Waqe Yurachman on the YouTube channel Physics World. You can actually watch his full lecture using the link right down in our description. So, we're going to explore exactly how alternating current behaves when we pass it through a simple, basic resistive circuit. If you've ever wondered how the power from, say, your wall outlet interacts with standard electronic components, well, you're in exactly the right place. We're going to break down the math, visualize the waves, and make the whole thing incredibly accessible. Let's get into it. So here's our roadmap for today. We'll start with AC circuits and resistor basics, move into voltage and current equations, then visualizing in-phase waveforms, vector representation, also known as phasors, and finally wrap it up with power and the power factor. All right, Section 1, AC circuits and resistor basics. Let's set some foundational rules. To really wrap our heads around AC, we first have to contrast it with DC. Direct current, or DC, which is what you'd get from a standard battery, flows in one single continuous direction. It's basically a one-way street. Alternating current, or AC, on the other hand, it's highly dynamic. It periodically reverses its direction and its polarity. So over one full cycle, a terminal that starts off positive will become negative, and then flip right back again. It's this continuous shifting, this constant back and forth oscillation that honestly makes AC so powerful and just incredibly fascinating to study. What's kind of wild here is the expanded cast of characters you find in AC circuits. See, in a standard DC circuit, the basic element you're dealing with is usually just the resistor. Simple enough, right? But when you step into the world of AC circuits, the lineup expands. You still have resistors, sure, but now you introduce inductors and capacitors, which react to that changing current in some really unique ways. But hey, don't worry about them right now. To truly understand the absolute foundation, today's explainer is going to maintain a laser focus on just the resistor. We're stripping away all that extra complexity to see the purest form of AC behavior. Moving right along to Section 2, voltage and current equations. Time to look at the math. Okay, step 1 begins right at the source, the AC generator. The voltage being pushed to our resistor isn't static, it's a sine wave. And the equation for this is V equals V0 sine omega t. Let's break that down, because it's actually pretty straightforward. V is your instantaneous voltage at any exact millisecond. V0 is the peak voltage, literally the absolute highest point that wave ever reaches. And omega t? That just represents the angle, which tells us exactly where we are in that alternating cycle at any given time t. Because it's a sine function, it perfectly maps out that smooth, undulating wave that rises, falls, and reverses. So, here's the crucial question. What happens to the current? Well, we apply good old Ohm's law. You probably remember this one. Current I equals voltage V divided by resistance R. If we divide our entire voltage equation by R, the math just translates beautifully. Our peak voltage, V0, divided by R, simply becomes our peak current, I0. And the result? We get our current equation, I equals I0 sine omega t. Noticed anything cool there? The sine function is exactly the same. The current is literally riding the exact same mathematical wave as the voltage. That brings us to Section 3, visualizing in-phase waveforms, or what I like to call a synchronized dance. Let's actually track one complete cycle through time using this table. We start our journey at time 0, where the angle is 0 and both voltage and current sit at exactly 0. Nothing is happening yet. As time moves forward to a quarter of the cycle, t over 4, our angle hits pi over 2 radians, which is 90 degrees. Right here, the sine function maximizes, and both our voltage and current leap up to their maximum positive peak at the exact same moment. Pressing on to t over 2, or pi, they cross back down through 0. At 3/4 of the cycle, they plunge to their maximum negative peak. And finally, at time t, a full 2 pi 360-degree cycle is complete, and they arrive right back at 0, ready to start the whole journey over again. And this brings us to a really massive takeaway. When alternating current flows through a pure resistor, the voltage and the current are doing this perfectly synchronized dance. They start at 0 together, they rise up and hit their maximum positive peaks at the exact same fraction of a second, they fall and cross the 0 line together, and they hit their negative valleys together. In physics terms, we say they are perfectly in phase. There is absolutely 0 phase difference or delay between them. Neither one is leading and neither one is lagging. They are totally locked in. But there's a key visual caveat here that you definitely need to watch out for. Just because they are in perfect phase synchronization doesn't mean their waves are the exact same height. Remember Ohm's law? I equals V over R?
If your resistance value is greater than 1 ohm, your peak current, I0, is mathematically going to be smaller than your peak voltage, V0. So when you look at a graph, the current wave will visually peak lower than the voltage wave. It kind of nestles inside it, even though their timing is flawlessly in sync.
All right, section 4, vector representation, which means we're visualizing phasors. So, instead of drawing a wavy line across a time axis, physicists have a simpler way to represent these alternating quantities, vectors, or arrows, rotating around a central point. We call these phasors. The length of the arrow represents the peak value, and its angle represents the phase. Because we just established that voltage and current are perfectly in phase through a resistor, their phasor vectors are drawn perfectly parallel to each other. They point in the exact same direction, visually proving a phase difference of 0. Imagine these two parallel arrows just rotating together smoothly along the axes, completely locked in step as the AC cycle progresses. Which leads us to our final stop, section 5, power and the power factor. Let's look at the real-world impact. This perfect synchronization between voltage and current, it's conceptually beautiful, but what does it actually mean for the real world? In an AC circuit, calculating the power that the resistor actually consumes isn't quite as simple as just multiplying voltage and current at any random moment. The foundational formula for electrical power in AC circuits is P equals V times I times the cosine of theta. Now that cosine of theta part at the end, that is incredibly important. In electrical engineering, this is known as the power factor. It essentially dictates how effectively the power is being transferred and utilized, all based on the phase angle, that's theta, between the voltage and the current. So, the crucial takeaway for our resistor is the result of that cosine calculation. It's exactly 1. Think back to our synchronized dance. The phase difference, theta, between voltage and current in a pure resistor is exactly 0 degrees. And if you plug that into a calculator, the cosine of 0 is exactly 1. This means the power factor of a purely resistive circuit is maxed out at 1. It is literally 100% efficient at converting that electrical energy into heat or light because the voltage and current are pushing in the exact same direction at the exact same time. Because our power factor is simply 1, it magically simplifies all our math right back down to the basics. Step 1, P equals V times I times 1, which, is just P equals V times I. Step 2, if we apply Ohm's law and swap out voltage for current times resistance, we get the classic power formula, P equals I squared R. Or step 3, if we do the reverse and substitute for current, we get P equals V squared over R. Because the AC is perfectly in phase through a resistor, we can literally just use these highly familiar standard electrical engineering equations to calculate the exact power being dissipated as heat. So there you have it. We've officially mastered the resistor. We know that when we push alternating current through it, voltage and current lock hands and perform a perfectly synchronized in-phase dance with a power factor of 1. But I want to leave you with a final provocative thought. If a basic resistor acts with such perfect harmony, what happens to this synchronized dance when we introduce something a little more complex, like a capacitor or an inductor? Do they stay in phase, or does one start to lag behind the other? That is a fascinating mystery and definitely one you'll want to explore in the next stage of your physics journey. Until then, keep asking questions, keep visualizing the math, and keep learning.